In this video, we're going to look at spherical coordinates. So this is another way of describing three-dimensional space. Let's start to draw some pictures and just introduce some notation here. So spherical coordinates are written in the order rho, phi, theta. And this theta here is the same as the theta we use in polar coordinates. So that one will be familiar. And we've got these new coordinates here, rho and phi. So let's draw a picture. Say we're in 3D, and let's say we want to represent this point here with spherical coordinates. All right, so rho represents the distance in 3D from our point to the origin. So there's rho, three-dimensional distance. Phi is always measured from the positive z-axis. So phi goes this way. And as we go through these coordinates, let's actually write down the range of values that each coordinate can take on. So because rho is a distance, rho is going to be non-negative. Could be 0 if your point were right at the origin. Could be positive, but it won't be negative. And for phi, phi is going to range between 0 and pi. So if we had a point up here, we'd have quite a small phi value. If we had a point down here, we'd have a phi value like maybe 3 pi over 4 or something like that, somewhere between 0 and pi. If we were looking at a point somewhere along the negative z-axis, then phi would be exactly equal to pi. And then we've got the same theta as we know from polar coordinates. So the way you would get that is you would drop your point down, just straight down vertically into the xy plane. And from there, you can think about theta. So you could think in the xy plane, the way theta is measured, it starts at the positive x-axis, which is over here, and winds towards the positive y-axis. That's the direction that it's going. So there's our theta. Okay, and then theta would be somewhere between 0 and 2 pi. So if you had a point over here on the left side of the diagram, you would actually be using a theta value that's somewhere bigger than pi to capture the left side of that diagram. You never need a phi value that's bigger than pi, because phi just represents how far you're tilting down from the z-axis. So you only need 180 degrees of tilt downward to capture that. And then theta lets you rotate around if you want to capture points on the left side of the diagram. So let's talk about some of the geometric relationships between our variables in case we need to convert between different coordinate systems. One triangle that's super helpful when we're working in spherical coordinates is the following right triangle. So I'm going to draw rho along the hypotenuse. That represents our distance in 3D. This vertical side length, let's call it z. So let's think of that as the z coordinate of a point that we're interested in. And this horizontal length here, we're going to call that r, because we can think of r as representing distance in the xy plane. So this is like saying if you take distance in your xy plane and then you build in z, then what you're getting along the hypotenuse is your distance in 3D. And the reason why it's good to draw the triangle in this orientation is because then we can put phi in here. See, phi is measured from the positive z-axis, so it makes sense to draw the triangle in this orientation. And then we can start to figure out some of the relationships between these variables. So we can say things like, well, from the Pythagorean theorem, rho squared is going to be z squared plus r squared. So we could say things like z is going to be rho cos phi, and we could say r is going to be rho sine phi. So that's just like saying rho is on the hypotenuse, we've got this angle phi here, and we're going to look at the vertical and horizontal sides of that triangle. One other fact that's going to be useful if we're ever trying to move between spherical and rectangular coordinates is that rho represents our distance in 3D. So rho is going to be the square root of x squared plus y squared plus z squared. So those are going to be the key relationships to remember anytime we're trying to convert between different coordinate systems. So in this example, we're going to be given some equations of surfaces that are written in rectangular coordinates, and we're going to re-express them in spherical. So let's start off with x squared plus y squared plus z squared equal 9. Okay, if we want to re-express that in spherical, we'd say, well, x squared plus y squared plus z squared is the same thing as rho squared. So rho squared equal 9 is now in spherical coordinates. All right, let's say we have the equation z equal 2 root x squared plus y squared, and we wanted to put this in spherical. So I think of cylindrical coordinates as being the middle ground between rectangular and spherical. So we could move into cylindrical by saying this root x squared plus y squared is r. And then once we've got that, we could draw our key triangle for spherical coordinates. So here's our z, here's our r, here's rho. We've got phi there, which is the angle from the positive z-axis, and then we can convert over to spherical. So z is going to be rho cos phi. R is going to be rho sine phi. We can divide through by rho to say cos phi equals 2 sine phi. And then we can do a little bit of rearranging here. So you could divide both sides by cos phi, and you'd end up with tan phi on the right side. And at the same time, you might want to divide through by 2. So you could say half equals tan of phi, or you could even go as far as saying phi equals arctan of 1/2. So if we think about the points in 3D that would have phi equal arctan of 1/2, well, let's say arctan of 1/2 is some angle that we're making with the positive z-axis, and we want to capture all the points that are sitting at that angle. So what we'd be capturing is actually a cone. It's an infinite cone. We could have any distance from the origin that we like. So rho could be anything that we like. Theta could be anything that we like. So that's allowing us to rotate around, but we're always sitting at that fixed angle, phi. So that's the equation of a cone. When you see phi equal something, that's a cone. And that's just another way of rephrasing this cone here. So last equation that we're going to express in spherical, we've got the equation z equal 3. So again, let's go back to our special triangle for spherical coordinates. We've got z, r, and rho there. So to get z into spherical, we're going to say z is rho cos phi. So we could say rho cos phi equals 3, or that might be rephrased as rho equals 3 secant phi. That's just like saying when you divide through by cos phi, you get this 1 over cos phi on the right side, which is the same thing as secant phi. So I'd say either of those is a good answer. The point is that we've rewritten our answer using only the spherical coordinates, which are rho, phi, and theta. Let's see if we can go backwards and express a certain surface in rectangular coordinates. The equation right now is written in spherical. Rho equals cosecant phi times cotangent phi. Okay, well, first thing I'd probably do is just write cosecant and cotangent in terms of cos and sine. So cosecant phi is 1 over sine phi, and cotangent phi is cos phi over sine phi. So I would like to multiply both sides here by sine squared phi, just to get rid of the denominators. So we've got rho sine squared phi equals cos phi. Okay, now we're starting to be on the right track. But if we think about our special triangle in spherical coordinates, let's draw that here. If we have any hope of going back to rectangular, it would probably be by moving through cylindrical coordinates. So we'd be trying to bring a z or an r into this discussion. So something like cos phi doesn't directly translate into cylindrical, but if we had a rho cos phi here, that would work. So what we could do is multiply both sides by rho. We could say rho squared sine squared phi equals rho cos phi, and then we're going to be in good shape, because on the left side we've got the square of rho sine phi. Rho sine phi is r. So in other words, we've got r squared, and rho cos phi is equal to z. All right, so we've got z equal r squared, and now that's easy enough to move back into rectangular, because remember from polar coordinates, r squared is equal to x squared plus y squared. So once we write it like that, we can say, oh, that's a paraboloid. Vertex at the origin and opening upwards. So that's our intro to spherical coordinates. Thanks for watching.